Diagat, Conas Tautu, hello and welcome. And I hope that wherever you find yourselves today, that you're keeping well and staying safe in these unusual times. Now this is mainly a revision video for my wonderful fifth years on the topic of heat and temperature. And these are topics that you've covered well, so you probably won't find this very challenging. Now I will normally begin these videos with a little checklist. So that at the end you can assess your own learning and see what you need to know and what you need to learn. So after watching this video, you should be able to do the following. You need to know the definitions of heat and temperature and the units that they're measured in. You need to know the definition of absolute zero and to be able to convert between degrees Celsius and degrees Kelvin. You need to know the definition of specific heat capacity, and you also need the units that specific capacity is measured in. You also need to know the formula associated with the definition of specific capacity for heat energy gained or lost by a substance. That's on page 58 of the maths tables, but you will get to learn it quite easily anyway. Water has a particularly high specific capacity, and there are advantages and disadvantages of this fact. You need to know one of each. And the last thing we did in class before the Christmas break was the experiment to measure the specific capacity of copper by the method of mixtures. And as you recall, you did this experiment exceptionally well. You carried out the experiment very well. The results you got were excellent. You did the calculations fantastically, and the final results were quite good. So for this experiment, you need to know a labeled diagram. You need to know the formula and be able to do the calculations from the formula. You need to know what measurements were taken and with what instruments. And you need to know about 5 separate precautions to make the final result more accurate. At the end, we'll be testing your knowledge by doing question 2 from the Leaving Cert paper from 2007. So let's continue. Now, our definition of heat is that heat is a form of energy. It will cause a rise in temperature when you add it to something, and it will cause a fall in temperature when you withdraw it. The unit of heat, of course, is the unit of energy, the joule. Temperature is a measure of how hot or cold something is. It's a measure of hotness or coldness, and we normally use the degrees Celsius, but sometimes we will use the Kelvin as appropriate. An analogy I often use is that you can have a coffee cup, a cup of coffee, at 60 degrees Celsius. You can have a swimming pool at 30 degrees Celsius. The coffee has a higher temperature than the swimming pool, but because of the exceptionally large volume of the swimming pool, it's got in total a lot more heat contained inside it. We have discussed the 2 temperature scales that are often used in science, the Celsius scale and the Kelvin scale. And in the real world, I think we're all very familiar with the Celsius scale of temperature. The Celsius scale of temperature is based on water and the freezing point and the boiling point of water. We attribute the temperature 0 degrees Celsius to the freezing point of water and 100 degrees Celsius to the boiling point of water. If you cool objects down, then you will come to a temperature that's very, very interesting. This temperature is minus 273.15 degrees Celsius on the Celsius scale. And at that temperature, interesting things begin to happen, or actually do happen. At this temperature, atoms actually stop vibrating. So it is a limit on the lowest temperature possible. It is, by definition, the lowest temperature possible, so it's known as absolute zero. So absolute zero is the lowest temperature that's possible, and it's minus 273.15 degrees Celsius. That number is actually on page 58 of your maths table, so you don't actually have to know it. In the late 1800s, Lord Kelvin said, well, let's start a new temperature scale that's based at the lowest temperature possible. And let's call that temperature absolute zero, or 0 Kelvin. If we go up then 273.15 degrees Kelvin, we come to the freezing point of water, and then above that by another 100 degrees is the boiling point of water. So the difference between the 2 scales will always be 273.15 degrees Celsius. To convert from one to the other, to go from Celsius to Kelvin, you add that number, and to go from Kelvin to Celsius, you subtract that number. You really don't have to remember that. You just always have to remember that Kelvin will always be a lower number than Celsius by 273.15 degrees. A very nice little example here. The temperature of outer space is around 3 degrees Kelvin, 3 Kelvin. What's this in degrees Celsius? Well, to go from Kelvin to Celsius, you subtract that number, minus 273.15. And when you do that, you get to a number minus 270.15 is the temperature of open space. That is pretty cold. That is pretty low, just 3 degrees above absolute zero. Now, central to our understanding of heat and temperature, of course, is the definition of specific heat capacity. Now, specific capacity is a measure of how much energy a substance can actually absorb or soak up into itself. And to give you an example, if you have 1 kilogram of copper and you want to rise its temperature by 1 degree Celsius or 1 Kelvin, you have to add 360 joules of energy to it. This number is known as the specific heat capacity of the copper. And the definition of specific capacity is the amount of energy needed to change the temperature of 1 kilogram of a substance by 1 degree. And its units are joules per kilogram per degree. Definition needs to be learned, so go and learn it. Another example is aluminium. Aluminium, obviously being different than copper, it has a different specific heat capacity. So if you have 1 kilogram of aluminium and you want to rise its temperature by 1 degree, you need to add 900 joules of energy to that 1 kilogram or per kilogram to rise the temperature by 1 degree. Water has a notoriously high specific capacity because if you have 1 kilogram of water and you want to rise its temperature by 1 degree, you have to add a whopping 4,180 joules of energy to the 1 kilogram of water to rise its temperature by 1 degree Kelvin. Water has a particularly high specific capacity, and we're going to see advantages and disadvantages of that fact very shortly. These are the more common specific heat capacities that you will encounter in questions. Copper 390, aluminium 900, water 4,180, and oil just about half that of water. It means oil only soaks up half the same amount of heat as water when you consider 1 kilogram. The units of specific capacity are joules per kilogram per degree. Very important to understand and learn those. Now, associated with that definition, we have the formula, and you've used this formula very well. And the formula tells you that if an object gains or loses energy, then the amount of energy gained or lost can be calculated by multiplying its mass by the specific capacity by the change of temperature. This formula will do if something rises in temperature, but it will also do if something is reduced or lowers in temperature. We'll see a couple of examples of use of this formula now coming up shortly. Okay, this is a pretty easy example. How much energy is needed to rise the temperature of 5 kilograms of copper by 25 degrees Celsius? The specific capacity of copper is given as 390 joules per kilogram per degree. Always note that mass should always be in kilograms. You are never wrong if you convert mass from grams to kilograms, and here we have the mass in kilograms. We'll see later that sometimes you can get away with using grams, but always remember that if you do convert to kilograms, you are never wrong. So we write down our formula. The mass is 5 kilograms, specific capacity is given as 390, change of temperature is 25. Multiply them out, you get 48,750. So it needs that much energy to do that. Similarly, if something drops in energy, if its temperature is reduced, you can also use that formula. The temperature of 5 kilograms of water is reduced by 15 degrees Celsius. How much energy this time has it lost? Well, you use the exact same formula. Write down the formula. Always start these questions by writing down the appropriate formula. Then do the substitution in. We've got the mass as 5, the specific capacity of water is given, and the drop in temperature was 15. Some people say, should I put in a minus 15 to indicate a drop in temperature? You can if you want, but that's rarely necessary. Multiplying out, and that is the amount of energy needed to drop the temperature of the water by those 15 degrees. Earlier we noted that water had a particularly high specific capacity. We said there were advantages and disadvantages of this fact. Well, give one advantage and one disadvantage. The big advantage of water having a high specific capacity is that it can soak up, absorb quite a lot of heat energy without rising very much in temperature. And that is very useful if you want to cool things down. For example, in a car engine, water is used as a coolant to cool the engine down. And in nuclear reactors, water is used in the reactor core to prevent the reactor getting too hot and taking the heat from the reactor core to make useful energy out of it. So there are two advantages of the high specific capacity of water. A disadvantage would, if you had a swimming pool, it would take quite a lot of energy to heat that swimming pool and quite a lot of cost. Or even if you're boiling a kettle of water, it takes a lot of energy to do that because water does soak up a lot of energy without rising too much in temperature. It has a high specific capacity. And the most important thing I think here that we're going to cover today is this experiment. And this experiment you have done it yourselves in groups of 2, you have done very, very well with it, so this should be just a little revision. Well, this is the experiment to measure the specific capacity of copper by the method of mixtures. You can also use this experiment to measure the specific capacity of water. They are quite interchangeable, and you'll see what I mean by that very shortly. Now in this experiment, what you basically do is you heat a known mass of copper. You get the mass on electronic balance. You heat them up, those little pieces of copper, small pieces of copper, up to 100 degrees Celsius. You can do that by putting it into a water bath and having an electronic heater or hot plate underneath. You heat the copper until it's at 100 degrees Celsius. A thermometer in the copper will tell you the temperature of the copper. And over here you've prepared a copper calorimeter of known mass. You measure its mass with the electronic balance. You half fill it with cold water. You then, by subtraction, get the mass of the cold water. And when you are ready, you transfer the hot copper into the cold water in the cold calorimeter. And at this stage, an energy transfer occurs. Something loses energy, that's the hot copper, and something else gains the equal amount of energy. That's the cold water and the calorimeter. So we can say the energy lost by the hot copper is equal to the energy gained by the water plus the energy gained by the calorimeter. Of course, some energy can leak out of the system. Some energy can be picked up by the surroundings, the air around the calorimeter. But we try to minimize that by using lagging, either cotton wool or polystyrene foam or something like that to insulate the calorimeter. We can also use a lid on the calorimeter to prevent too much energy being lost to the air. Another way we minimize heat loss in this experiment is we use a thermometer of low heat capacity. That means the thermometer doesn't absorb or steal very much heat from the water that it's measuring the temperature of. More about that later. But in essence, we can say the energy lost by the hot copper equals the energy gained by the water plus the energy gained by the calorimeter. Now the maths behind this experiment are pretty easy. As we said earlier, the energy lost by the hot copper equals the energy gained by the water plus the energy gained by the calorimeter. We know the mass by measurement of the copper, we know the mass of the water, we know the mass of the calorimeter using the electronic balance. We can work out the changes in temperature of each of these things using the thermometer, and we simply equate all this together. The mass by specific capacity by change in temperature of the copper equals the mass by specific capacity by change in temperature of the water plus the mass by specific capacity by change in temperature of the calorimeter. Remember, the calorimeter is made of copper, so we know that number. The specific capacity of the copper and the specific capacity of the calorimeter, of course, will be the same number. And the change in temperature of the water and the change in temperature of the calorimeter, they will also be the same number because the water and the calorimeter are together at the start, they're together at the end, so the rise in temperature will be the same for each. In a question that you'll be doing shortly, you will be using that formula. But of course, you need to learn it. In all these experiments, there are a set of precautions to make the final result more accurate, and a lot of these precautions will do for any experiment in heat whatsoever, and they become tedious after a while, but they're worth learning because obviously they come up quite a lot in Leaving Cert questions. A lot of them are about minimizing heat loss to the surroundings, so let's run through a few of them. Well, first of all, you should lag the calorimeter with something like cotton wool or polystyrene foam or something like that. By the way, polystyrene, some people ask me, what is polystyrene? Polystyrene is that material like that coffee cups, that white material that coffee cups and things like that are made of. So you lag the calorimeter to prevent heat loss to the air, to the surroundings. Put a lid on the calorimeter also will do the same. It will prevent heat loss to the air. You can use a more sensitive thermometer. And what does that mean? Well, it measures to more places of decimal. Better still, you can use a thing called a digital thermometer that normally measures to 1 or 2 places of decimal. You notice I like to give the precaution, like use a more sensitive thermometer, and also in the same sentence give the reason that we use that precaution to measure to more places of decimal. That makes your statement a lot more powerful. And it can answer a question that you might not have seen in the actual exam. Use a thermometer with low heat capacity. That's the precaution. What does that mean? Well, that means the thermometer doesn't absorb very much heat from the water. It will minimize the heat that is absorbed from the water that you're trying to measure the temperature of. Another precaution is to polish the calorimeter to minimize heat loss by radiation. It's a very theoretical one, but it should work. And of course, transfer the copper pieces quickly to minimize heat loss to the air, to the surroundings. Just a few little questions I've seen crop up in exam papers, both real exam papers and pre-exam papers. We'll just run through them fairly quickly. Why are copper pieces used? Remember when you did this experiment, you actually saw very small copper pieces rather than just one large lump of copper. Well, why copper pieces, not just one large lump of copper? Well, copper pieces will have a larger surface area. That means they will lose heat a lot quicker when you put them into the water. So heat is transferred quickly to the water. That, of course, minimizes any loss to the surroundings, to the air. This came up in the Leaving Cert paper only a year ago. Or was it this year's paper, actually, then to 2020, which was done quite recently by students. How was the copper calorimeter insulated? Well, you can say any insulating material whatsoever. Cotton wool around it will do perfectly, or polystyrene foam around it, or piece of carpet, or anything will do it. But cotton wool or polystyrene are two very, very good answers of how it is insulated. Why is a thermometer with a low heat capacity used? Well, we use a thermometer with low heat capacity, so we will minimize the heat lost by the water and absorbed by the thermometer. And the question that has come up more than once is, how did you know that the copper pieces were initially at a temperature of 100 degrees Celsius? These copper pieces that we used in our experiment, how did you know that those copper pieces were initially at 100 degrees Celsius? Well, the easiest way is to have a thermometer in the test tube, and that tells you they're at 100 degrees Celsius. But if you also said they were boiling in a water bath at 100 degrees, boiling water for a sufficient length of time, they will obviously come to 100 degrees Celsius as well. Okay, now we're going to have a very quick look. We said at the end we would do a Leaving Cert question. And this is the Leaving Cert question. It's from the Ard Taishless Ard Levéal, the Leaving Cert Ard Levéal Higher Level paper of 2007. It's a pretty straightforward question. I don't think anyone's going to have too much trouble with it, but it's a Leaving Cert honours question, so you have to pay it respect. It says the specific heat capacity of water. Remember I said earlier you can change this experiment for specific capacity of water or copper. The specific capacity of water was found by adding hot copper to water in a copper calorimeter. The following data was recorded. So it gives you the mass of the calorimeter and the mass of the calorimeter when you've added the water to it. Now I better say something straight off here. We are going to leave all our mass measurements in grams. And you will say, hang on, a few minutes earlier you said you're never wrong if you convert from grams to kilograms. That remains true. But if you go back to our formula here and have a quick look at the formula again, you will notice that the formula has 3 parts. 1, 2, 3, and each contains mass. That means if we put in the mass values as grams, then everything will even out and we will get the exact same correct answer and there will be no problems. And students tend to prefer to put the masses in as grams because it gives them easier numbers to actually work with. So we're going to leave them as grams. There's 3 other experiments in heat. We hope to do them when we get back to reality, but we're going to go through them here, at least in theoretical videos for a while. And we're going to find that in most of those experiments, 2 out of the 3 experiments coming up, we can also do exactly the same, leave everything in grams. There's one we can't, and we have to bear that in mind too. Let's get back to the question. Mass of calorimeter plus water, subtract those 2, you've got the mass of your water. Mass of calorimeter plus water and mass of calorimeter plus water plus copper. By subtraction there, you can also get the mass of your copper. The initial temperature of the water was 16.5 degrees. You added the hot copper, the temperature went up to 21 degrees. So we can work out the rising temperature of the water in the calorimeter, and that would be the same as the rising temperature of the calorimeter. The hot copper went down from 99.5 degrees down to 21 degrees, so you can work out the drop in temperature of the hot copper. And I actually like to, and we're given the specific capacity of copper and we're looking for the specific capacity of water, I like to do all this kind of working out first. And I'll just show you what I've done here, starting off when I've done the rest of the question, but we'll do the maths part first. We'll stick to the maths part first. What I did was I did all my working out like this first. I worked out the mass of the calorimeter was given. By subtraction, I got the mass of the water. By subtraction again, I got the mass of the copper. I got the changes in temperature of the copper, the change in temperature of the water, which is equal to change in temperature of the calorimeter. I think you should always do that working out and show your work, because it sets you up very, very nicely for the rest of the question. Looking at the other parts of the question, describe how the copper was heated. A diagram there of the copper pieces in the test tube in the water bath will do grand with some device, a hot plate or an electronic heater below it. How is its temperature measured? Obviously with a thermometer. Give 2 precautions that were taken to minimize heat loss to the surroundings. Now we've discussed several, so if you're ever asked for 2, try to give 3, don't give 4. So try to give 3 precautions for that part. Explain why adding a larger mass of copper would improve the accuracy of the experiment. If we used more copper, if we were back here and instead of using, let's say, 50 grams of copper, we used 100 grams of copper, why would that give more accurate answers? Well, if you use more copper, if you use a larger mass of copper, what will be larger over here? Well, obviously the water will pick up more energy and the rise in temperature of the water will be more. And we'll be dealing with bigger numbers. And we've said this many times, if you're dealing with bigger numbers, that reduces a certain type of error. Can you remember what kind of error is reduced if you deal with bigger numbers? So my answer to that little part there would be something like the final part there of the question. If you use a larger mass of copper, that will cause a larger rise in temperature of the water, and that will reduce a certain kind of error. I'm not going to tell you, you should be able to remember it. I'm now going to ask you to go and do that question and the full amount of it, and then when you're finished, of course, come back to the video and you'll find that I've got the answers here. There they are. I've also got a little bonus question at the end, and this is kind of a tough one. Actually, it's not too tough to start it off, but it's tough to get the right answer at the end. It looks an innocuous, easy enough question. Let's go through it. 80 grams of copper at 100 degrees Celsius is added to 200 grams of water, which is at 25 degrees Celsius. It's in a polystyrene cup. We can assume that the polystyrene cup will not absorb any heat, that it's got a low heat capacity, and we want to calculate the final temperature of the mixture. We're given the specific capacity of the copper and the specific capacity of the water there. I am a visual thinker. I like to see diagrams and they help me to understand what's going on. So here we are, 80 grams of copper at 100 degrees Celsius, 200 grams of water at 25. We dump the copper in. So the temperature of the mixture of copper and water will be obviously bigger than 25 because the water will go up in temperature, and below 100 because the copper will come down in temperature. Let's call this new temperature of the mixture X degrees. Now we can, of course, work out the changes in temperature. The copper will come down in temperature, so the change in temperature of the copper will be 100 minus X. The rise in temperature of the water will be X minus 25. The water started at 25, it'll go up to X. X could be 35, so 35 minus 25 will be 10 if the water goes up by 10. And then, of course, we can actually put this down in writing. The energy lost by the hot copper will equal the energy gained by the water. We can then put formulas onto that and work out the answer, which is contained further down in the video. But if you do feel adventurous and you have the time, you might as well do that extra question as well and test yourself to see how you get on with it. Now what I'm going to do is just scroll up in the video so you can see the answers to the Honours Leaving Cert question, and then I'll scroll down to see the answer to this bonus extra question, and hopefully you'll get something out of that. You, of course, can pause the video at any stage whatsoever so you can read this. Obviously, I'll upload these to Teams as well. I do appreciate this has gone well over 25 minutes, and I would prefer to keep my videos shorter, so I will try to do that in future. Okay, so that's the Honours Leaving Cert question, that's the answers. And here's our bonus question. To me, the most important part was setting it up like that. Say, what is the change in temperature of the copper? What's the change in temperature of the water? Let X be the new temperature. We then know that the copper will go from 100 down to X. The water will go from X, or from 25 up to X. And they're the changes in temperature. You can then say energy lost by the copper equals energy gained by the water. The calorimeter doesn't come into it because it's polystyrene. It doesn't absorb any heat. We're told that in the question. And here is my answer. It wasn't a bad question down as far as about here. And that's where most of the marks would have gone for. Then it's just basically algebra and mathematics after that. But the numbers got big. The numbers got big and awkward. And it's a question I have not seen on a Leaving Cert paper, so don't worry too much about it. But if you can do it, fair dues to you. That's the answer I got. Hopefully that was the correct answer. And sorry for going well over time here. I promise not to do that in future. Anyway, at the end of this, you should go back up here. You should go back up to my little checklist. See all those definitions. Have you learned them? See all those definitions. Have you learned them? The experiment. Do you know those things? And how do you know those things? Well, by actually doing questions and by actually writing these things out. Take care, and we'll see you again later. Slán.